In this lecture, we're going to finish analyzing the runtime of MergeSort, which we started discussing during last time's lecture. And the setup we had last time was that we assumed that we had a subroutine called merge that took an array A and three indices A, P, Q, and R. And what merge did was it assumed that it had two sub arrays. So it assumed that it had A from P to Q and A from Q plus 1 to R, and that these two subarrays were already sorted. And what merge did was it combined them into a single subarray from P all the way to R that was sorted into one single big array. And what we did was that we said that if we had that merge subroutine, we could do sorting for a big array by using the divide and conquer methodology and basically do a recursive call to merge sort. And what we said was we could do the following. We could have merge sort, which would sort a big array, and it would have an array with the first index and the second and the last index. And what we would do was we would check if P was strictly less than R. And if that was the case, then we would find the midpoint, which would be Q, the floor of P plus R divided by 2. And that would be Q. And basically that would divide the array A into two different arrays. And then we just called merge sort on each one of the parts of that array. So we would just say merge sort the first part, do a recursive call of that from P to Q, and then do another recursive call of merge sort from Q plus 1 to R. Now once we have those two calls of merge sort, then we end up with two sorted subarrays, and then we just now call this merge subroutine for A, P, Q, and R. And after we did these three steps, we would have a sorted array of size from P to R. Now, what these two steps do is it's a recursive call of the thing on smaller subarrays. And the general idea, as we discussed before, was that the merge sort would something like this. We would start with a big array. We separate it into two smaller arrays, and then recursively call now merge sort on this smaller array, separate it into two parts, and keep doing it. And then at the end, once we have things that are sorted already because they're only one element, so it takes us constant time to do that, to sort this array because they're only one element, then we would combine them into a bigger array using this merge. And again, we would do that again with the two bigger parts until we do the large merge into a single array. So that's the main idea behind merge sort. And really, what we wanted to say is, well, we want to analyze how long it's going to take to run each one of these this call of merge sort. How long is it going to take? Assuming that the amount of elements from P to R is n, so we have an n size array. So the way we're going to do this is we know that this line, the Q, takes constant time. And we need to figure out how long is it going to take to do each one of these merge sorts on a smaller scale, and how long does it take to do the merge. And we talked a little bit about the merge and how we would do the merging of two already sorted arrays into a single array. And what we mentioned was that what we would do is just look at the first look at the first index of each one of the arrays. And whichever one was smaller, that's the one we're going to add to the big array. And then we increase the index of that array where we took the smaller element. And now compare the two arrays, whatever the index is pointing to. So what merge is going to do is going to be the following. We're going to have two subarrays, and the first thing we're going to do is we're going to find how big each one of the subarrays is going to be. One is going to be n1, the second one is going to be n2, and then we create two subarrays that have one more element than the size of each one of the smaller subarrays, and we'll see why we have that extra one in a little bit. Then all we do is we call one of the arrays that we created, we call it L, the other one we call it R, and then what we're going to do after that is we're going to move all the elements from the array A into L for the first part of it, and then into R for the second part of it. So we just have N1 and N2 elements in L1, L and R respectively. And the last element, that plus one element, is going to be filled with infinities, because what we want is, if we've run out of one of the arrays, we just want to keep the procedure going until we finish everything else from the other array. So what we do is really, this is the bulk of it. We start two counters, 2 pointers to the index of each one of the arrays, I and j. And what we're going to do from P to R, we're just going to check what's going to happen. We're going to check if the left one or the right one is smaller. And if the left one is smaller, then that's the one we're going to add into the array. And then we increase the counter for L by 1. Otherwise, the one that we're going to add to A is going to be R, and then we're going to increase the counter of R by 1. Now, how long does this take? Well, it's easy to see that this first part takes order 1, so that's constant time. Creating these arrays and filling them out takes order n. These two lines take constant time, along with these 2 lines as well. And then the for loop is going to run for order n times, and each one of those is just a check if which one is smaller, and then adding one entry into an array. So each one of the for loops is going to be constant time, so the whole thing takes order n times. Now the big question is, what we have is that this merge procedure takes order n. Now the big question is, how long does it take to run each one of the merge sorts? Well, the main thing that we have to think about is that now we don't know exactly how much the smaller merge sort is, because we're trying to figure out how big the large merge sort is. So all we know is that each one of these merge sorts that we're trying to consider are just performing tasks on an array that is half as big. So the way we're going to analyze this, and this is the way we're going to analyze most of our divide and conquer algorithms, is we're going to do the following. We're going to set up a recursion. So the runtime of MergeSort we're going to say, how long does the whole thing take? So we're going to let t sub n be the runtime of MergeSort. And we don't know what that is yet. We don't know what that is. But we're just gonna say it's T sub n. From this, we can say that the total runtime of MergeSort consists of two things of smaller size, the same runtime but on smaller times, and something that is order n. In fact, it's not just order n, it's theta of n, because we know that is exactly gonna take us n to run. So we could say that t sub n is 2 times the same runtime, this t, but instead of being of size n, it's of size n over 2, plus theta of n. So this is a recursion. This is this is going to be our key to analyzing divide and conquer algorithms. We're going to write the runtime of each one of these algorithms as not just basically with a recursion. So we're going to have that t of n is going to be equal to 2 computations of something that is half the size, plus some amount to combine them. And this can also be written as t sub n is equal to 2 t n over 2 plus some constant times n, because we know that our runtime is just some constant because it's theta of n. So it's just a multiple constant of a function that is just n. So with this formulation in mind, now let's consider the following, okay? So consider the following analysis of accounting of how much each time the whole merge sort is going to run. How much work we have to do for that. So consider the following. What we're going to do and to analyze how long merge sort is going to run is that we know that at the end we have to do a constant time times n amount of work to combine two different. So that's the amount of work that we're going to have to do, which is this merge, right? Which is a constant time times n, and the total amount of work is going to be constant time times n plus all the amount of work that needed to be done to compute merge sort of one of the halves and the amount of time spent trying to do merge sort on the other one. So we know that it's going to be C of n plus the amount of work taken to do the first half. So let's say this side is going to be the amount of work done to compute the first half of the array, to sort the first half of the array. How long does it take to compute the first half of the array? Well, for that, it's going to be C of n divided by 2 to merge plus the amount of work to compute the first fourth of the array and then the second fourth of the array, right? So the first half of the array is going to be constant time times n over 2 plus the amount of work taken to do the first fourth and the second fourth. And how long does it take to do the first fourth? Well, it's going to be constant time times n over 4 plus the amount of work taken to do the first 8 plus the second 8. And so on, right? So that's you could start seeing a pattern here. So to do the first half is constant time times n over 2, but then plus the amount of work to compute the first fourth and the second fourth. And then the second fourth is also going to have amount of work, constant time times n over 4, times the amount of work to compute the first 8 and then the third 8 and the fourth 8, right? And the pattern is that at each level we could count the amount of work by saying the amount of work total amount of work we're going to do is this amount of work plus everything else that is below it. So we have this binary tree where at each layer we could figure out how much work we're doing. And we keep moving this tree until when? Well, we keep doing it until the leaves, the amount of work that we're going to have to do at the leaves is constant time. It's basically just, it's just going to be one amount of work. So now we could do the total accounting of the amount of work that we're going to have to do. So let's say we're at level, this is going to be the level, and this is the amount of work we're doing at each level. So at level 0, we're going to make the amount of work is just going to be one of these C of n's. So there's going to be C of n amount of work, C times n amount of work. Then at the first level, we have 2 of C n divided by 2. So the total amount of work is going to be Cn. And at the second level, we're going to have 4 of this Cn divided by 4. So the total work is C of n. And we're going to do that. And so at each level, we're going to be doing a total amount of work that is C of n, a constant times n. Now, the big question is going to be, how many levels are we going to have? Well, because it's a binary tree, we know that the height is going to be, we start with n levels and we're doing all the way until we have one entry on each one of the levels. And all we're going to do there is just going to be just one amount of work. So the amount of levels that we're going to have is going to be log base 2 of n. So that's the amount of work that we're going to do. So we have log base 2 of n levels, and each level is doing a constant times C of n of work. So the total amount of work that we're going to do is going to be log base 2 of n times a constant times n, which means that this is order n log n. So MergeSort, when we do accounting of all the amount of work that we're going to have to do, runs in order n log n. And we know this is good because we know that sorting can be done in n log n. So now what we've done is we've found another way of doing sorting, another approach, and another approach to analysis by doing this recursion right here. And then when we add it up, we realize that we do the same amount of work as we do in, for example, heap sort and those sorting algorithms that do comparisons of nodes. And that's good because we know that the best we could hope for runtime for any comparison-based sorting algorithm is going to be n log n. And this is what we have with this. Okay, so now that we have this tool of writing the runtime of a divide and conquer algorithm as a recursion, we're going to use a very powerful tool that is going to give us basically the solution to what is the runtime of any divide and conquer algorithm. And that tool is called the master theorem. And what it says is the following. It says, let A be greater than or equal to 1, and B be strictly greater than 1. and those two are constants. Then let f of n be a function, and let t of n be defined by the recurrence t of n is that constant a times t n divided by b plus f of n. Now what this means is that we could rewrite a recursion as some number a of computations that are some fraction smaller than the original one. So divide and conquer is going to break our problem into smaller subproblems. And what that means is that we're going to have a subproblems that are smaller by some fraction b. And then it takes some f of n amount to combine those solutions. That's the idea behind this. So the master theorem says we have this recurrence t sub n equals at of n divided by b plus f of n. We say then t of n can be bounded as follows. We're going to have several different cases about what the bound for t of n is. And the first case is the following. If f of n is equal to some, it's big O of n log base b of a minus some epsilon for some constant epsilon greater than 0, then t of n is going to be theta of n log b of a. Now we're going to deal with a little epsilon later. We'll get to an example. For right now, just know that if f of n is big O of this amount, then theta, the t of n is going to be theta of log base b of a. Second case is if f of n is theta of n log base b of a, then t of n is theta of n log base b of a log n. And then the third case is if f of n is lower bounded, that is this omega of n log base b of a plus some epsilon for some epsilon greater than 0, and f of n divided by b is less than c f of n, then t of n is equal to theta f of n. Now, these three cases seem a little arbitrary and there's not a lot of intuition behind them. And that's the case with the master theorem. In reality, there's not a lot of intuition behind each one of these approaches. It's something that we're going to be using and we're going to be useful, and we're not going to prove actually the master theorem, but we're going to be using it. And this is a very important tool and a very useful tool because it tells us pretty much, it covers a great chunk of runtimes of divide and conquer algorithms. Algorithms where we're going to be doing recursive calls of our function on smaller sets. So let's do some examples just to kind of illustrate how we're going to be using this master theorem, because that's really what is going to be important. So let's say we have the example that we saw in actually MergeSort, right? So let's say T of n is 2t n divided by 2 plus theta of n. And we know what T of n is going to be. We know that the runtime is going to be n log n. So let's see how we use the master theorem for there. What we care about, so we're always going to be comparing, we care about always kind of the comparison between T of n, sorry, not T of n, f of n versus n to the log base b of a. And the reason why we always care about this things to comparison is because if you see the master theorem, we see that we were checking is f of n big O of this value, f of n theta of that value, or f of n omega of that value, plus those epsilons. And I said we'll talk about the epsilons in a little bit. So what we care about is that. So what is f of n? So we know in this case f of n, we know in this case f of n is theta of n. And we have our n log b of a. B in this case is 2 and a is 2. So we have n log base 2 of 2, which means just n. So now we compare theta of n with n. And we see that basically f of n is theta of n log base 2 of a. We see here, we say f of n is theta of n log b of a. So we have this case in this scenario. So we have that in this scenario, because these two comparisons, f of n is theta of n log base b of a, we know that we are dealing with case 2 in our master theorem. So we have case 2, which is that, which says that T of n is going to be theta of n log base b of a log n. So we know that T of n, the runtime, is going to be theta of n log base 2 of 2 log n, which means it's theta of n log n, which is what we expected, as it should be. So that's how we're going to be using the master theorem. So that's an example. So let's do another example. Now let's say T of n is going to be 9t n over 3 plus n. Again, we care about f of n versus n log base b of a. Now f of n in this case is n, and we're going to compare it to n log 3 of 9, which is n squared, because the log base 3 of 9 is n squared. So what do we know? How does f of n, which is n, compare to n squared? Well, it's an upper bound. And so we say is that f of n is upper bounded by n log 3 of 9. But not only is it upper bounded by that, which is upper bounded by n squared, it's upper bounded by n squared minus a little bit, because n is upper bounded by n squared and a little bit below 2. Epsilon could be anywhere between 0 and 1. So we could find an epsilon and still find it that it be true. So we know that it's upper bounded. F of n is upper bounded by n log base 3 of 9 minus some epsilon, which is this right here. So now we know that the runtime is going to be it's going to be theta of n log base b of a. So what that says is that the result is that so we say case 1 because we're upper bounded. So we have case 1 here. And because it's case 1, we say that T of n is theta of n squared. Or just to be more explicit, n log base 3 of 9, which is theta of n squared. So that's going to be a runtime of something that would create 9 subproblems, each one having a third of the problem of the size. Okay, so if we have a situation like that, we know that our runtime is going to be n squared. One more example. Let's keep going with the examples. So let's say we have that our runtime can be expressed as t 2n divided by 3 plus 1. Again, we want to compare f of n versus n log base b of a. F of n is 1. And what is log base b of a? So it's n log b is 3/2. Sorry. B is 3/2 and a is 1. So what is log base 3 of 1? Well, any base log of 1 is 0, so it's n to the 0, which is 1. So we have comparison of 1 to the 1. We know that f of n, which is 1, is theta of log base b of a, which is also 1. So we have that f of n is tightly bounded by our log, which again brings us to case 2. So we say case 2, and with case 2 we know the answer. It's right here. So the runtime T of n is equal to, we look it up, theta of n log base b of a log of n. So theta of n log base b of a log n, which now means that this is theta n log b of a is 1, so it's just log n. So our runtime is going to be theta of log n. Let's do 2 more examples. First example is going to be, the next example is going to be T of n 3 T n over 4 plus n log n. What is f of n? That's the things that we need to compare. F of n is n log n. What's n log base b of a? Well, it's n log, what is b? Is 4, and a is 3, which is equal to n And this number, log base 4 of 3, is actually 0.793. And now what we say is, how does this value compare to this value? Is it upper bounded by that? Is it lower bounded by that? And we see that this value is a lower bound for this value because this n is to the power 1, and this one is a power that is less than 1. So we know that this value is a lower bound for this. So we know that f of n is lower bounded by n 0.793, and not only is it lower bounded by n 0.93, it's lower bounded by n to the 0.793 plus something. We could find a little epsilon that is positive and still below 1. Okay, so then we have, because of that, because it's lower bounded, we know that we're looking at case 3. And for case 3, we see that t of n is just f of n. So we have case 3. So we have t of n is just theta of f of n. And we know what f of n is. So then this is just theta of n log n. And that's going to be a runtime. Again, the main idea behind the master theorem is that this is a useful tool because we could come up with our recurrence that's going to be easy to do, and then now we have the master theorem to calculate the runtime. Now, let's do one last example that is going to figure out and is going to point out that issue with the epsilon, right? So let's say we have a runtime that is 2 t n over 2 plus n log n. Now f of n is n log n, and n log base b of a is n log base b, log base 2 of 2, which is just n. So now the question is, how is log n and so how is n log n and n related? So we could say that f of n is lower bounded by n log base b of a, which is it's lower bounded by n, because f of n is n log n, and n log n is lower bounded by n. Now the big issue here is that n log n is lower bounded by n, but it's not lower bounded. It's not lower bounded by n log base 2 of 2 plus some epsilon, which means it's not lower bounded by n1 plus some epsilon. Why? Because as soon as we have a power of 1 that is bigger than 1, that polynomial of something bigger than 1 is going to be bigger than n log n. It's going to be an upper bound. So because here it is lower bounded by n log n, but not lower bounded by n plus some epsilon, we cannot use the master theorem. So we can't use master theorem. Okay, so the last thing I want to talk about today is another example of divide and conquer, where the divide and conquer approach helped us out to improve on sort of common techniques of approaching a problem. And to do that, we're going to do matrix multiplication, which is another way that we could do another problem where we could use divide and conquer and get some gains. So think about how we do matrix multiplication. So suppose we have two n by n matrices, and we want to multiply those two matrices to compute the product C of each one of those. So suppose we're trying to do that, and in order to do that, what we're going to have to do is we're going to have to compute each one of these elements of C by doing multiplication. We're going to do this row times this column and then add it all up. So think about how many operations we're going to have to do matrix multiplication using our regular techniques. So we have to compute each one of the entries of the matrix. So we have a total of n square entries on this matrix C. So each one of these numbers is going to be an entry, and we have n square entries. Now, per entry, how many operations are we going to have to do? Well, we have to do A1 times B, A11 times B11, and then A12 times B21, and so on. So we're going to have to do n of these multiplications, and then add them all up, which is going to be n minus 1 additions. So in total, we're going to have to do around order n operations to compute each one of these numbers. Now, because of that, we have n squared numbers that we have to compute, and each one takes about order n operations. We could say that brute force is going to take order n cube operations. Now the question is, are we going to be able to do any better than that? Well, the answer is probably yes, because divide and conquer is going to give us maybe some gains. So what we're going to do is let's try to do it with divide and conquer, and see if that's going to give us any gains. So let's start. Maybe one thing we could do is divide A and B into 4 n 1/2 or n over 2 blocks. So we have n divided by 2 by n divided by 2 blocks. So this block 1 consists of a n divided by 2 by n divided by 2 sort of block. And then we have another one, and then we have another one, and we have another one. So we have 4 of this n divided by 2 blocks. N divided by 2 by n divided by 2 blocks. So it turns out, which is really nice, that when we multiply this first block, as we consider as a matrix, a submatrix, and we multiply this and this by this and this block, so basically the blocks in the first row times the blocks on the first column, and then we do the addition, we get the result for this. These are no longer, each one of these ones, of these blocks that I circled, is no longer a single element of a matrix. It's a block of half n by half n blocks. Half n by half n entries. So to compute this C1, what we have to do is do this matrix times that matrix, and then this matrix 1, 2 by this matrix B2, 1. And we add those two resulting matrices. So these are the two multiplications, these two matrix multiplications that we have to add to get this result. And then we add these two matrices. Now that seems very promising, because what we have now is that we could get the result by adding smaller matrices, by adding products of smaller matrices. So now what we're doing is we're multiplying two smaller matrices and then another two smaller matrices and then combining them. So what we have is now we have 8 multiplications that we have to do and some additions, right? But each multiplication that we have to do is on a smaller matrix. Now, how much is it going to cost us to do all this work in that? Well, now we have this idea of the recurrence that we could do. So we could say, how long is it going to take us? Well, the amount of work that it's going to take us is going to be T of n. We're going to be doing 8 multiplications rather than just 1. So we're still going to do multiplications, but we're going to be doing multiplications on smaller sets. So it's going to be n, 8 of the amount of time it takes, but now to do only n over 2. Plus, and then how long is it going to take us, once we have those multiplications, how long is it going to take us to combine them all together? We're going to do additions. We're going to have to do additions. And for additions, we still have to do compute by adding up each one of the elements of this big C matrix. And this big C matrix still has n square elements. So we're still going to have n square elements and additions that we're going to have to add to compute. And it's going to be in the order of that. It's a constant times that. So what we have is that we have our recurrence. So we're going to have a times t n over 2 plus theta of n squared. Now, if we think about this, we're going to look at our master theorem, and we're going to see which one of the cases does this fall under. So again, we're going to compare theta of n squared, because this is our f of n. And then we need to compare our n log base b of a, which is n log base 2 of 8, which is n cubed. And we're going to say, how does fn compare to this n log base 2 of 8? And we're going to see that we're going to have that f of n is upper bounded by n log base 2 of 8 minus some epsilon. If it's bounded by 3, it's also bounded by something a little bit less than 3. Which means that we're in our first case, and when we're on our first case, we realize that we're just back to being bounded by f of n, which is n cubed. Okay, so we know that our runtime is going to be order n cubed when we do this division, which actually turns out to be pretty sad. Because that's exactly what our greedy algorithm was giving us. Our brute force algorithm was giving us. So just computing them has exactly the same runtime as doing this divide and conquer approach. So here we have an example where we're doing divide and conquer, but it's not really gaining us anything over just the brute force algorithm. But, of course, there is a smarter way to do this. And what we're going to see is that, again, we could calculate, we're going to break our matrices into n divided by 2 by n divided by 2 blocks, right, into 4 of those, to calculate our 4 blocks that are going to make our C matrix or resulting matrix. But this is very important, that we could figure out what C11 is by a strange combination of sub-matrices that don't have a lot of intuition, but it turns out that C1 is equal to this summation of these P's, or these P matrices, where each one of those P matrices is, so P5 is this, P4 is this, P2 is this one, and P6 is that. So this is actually a very, very interesting result that says that you could compute each one of the blocks C11, C12, C21, and C22 by computing this 7 piece. And those 7 pieces, each one of those only has one multiplication. See, they're multiplications and additions of matrices. This is very, very, very interesting because that means that when we have this multiplications, we shouldn't be calculating C11 directly. We could calculate each one of these P1 through P7 directly. And then once we have those P1 through P7 directly, we're going to be able to capture or calculate each one of those C blocks of n divided by 2 by n divided by 2 entries. Now, why is this important? Because to calculate this piece, the 7 piece, all we have to do is just do 7 multiplications. And 7 multiplications is one less multiplication than what we had to do before. And that is promising into telling us which one it's going to be. So now our runtime, we could say T of n is going to be now only 7 multiplications. 7 multiplications, each one of size n over 2 of size n over 2, and then still just having to do all the entries and combine them. We have to add each one of those n square elements. And that, now we're going to see that this is going to have a better solution. So this approach is exactly what Strassen came up with in 1969, and this is one of the fast multiplication algorithms. So what we do is we divide them into those blocks. We compute different matrices. So we compute, right here it says that we compute 14 matrices. This is one matrix, this another 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 matrix. And the amount of cost that it takes is 10 matrix additions to do that. And matrix addition is going to be n squared work. And then we do 7 multiplies. And that's the key, because that is going to give us this recursion right here. And because we're going to have that recursion there, we could use our master theorem. Now again, what we have to compare is going to be f of n, which is theta of n squared. And we're going to do n log base 2 of 7, which turns out to be it turns out to be n to the 2.81. Now, again, we now see what is the relationship between f of n and n log base 2 of 7, and we see that f of n is upper bounded by n log base 2 of 7, which implies that our runtime is going to be theta of n to the 2.81. And it turns out that this order n 2.81 is faster than our brute force algorithm, which was order n cubed. And that shows that this is an important gain into doing fast multiplication. Now, it doesn't seem that much because we're going from 3 to n to the 2.81. But when n is large, when you have matrices that are n by n and their n is really large, that amount of time is quite significant.